talk. Your talk really changed our thinking about energy and the system. Okay, let me ask you a simple question. You talk about copper chlorine cycles, right? Looks so interesting. Any guy commercialize this kind of system to generate hydrogen and oxygen from seawater? And commercially,
ACL is trying to do it. Okay.
So far, not available yet.
There are many salt cycles. Okay? There's one involving sulfur and iodine, but it needs to get to higher temperatures. So it needs a more capable reactor. Right now, we're just talking about relatively mild temperatures. So that sulfur iodine cycle doesn't need any electricity input. You can just do it thermally. But it's much more challenging for nuclear reactors. People are trying to build such reactors, advanced high temperature reactors. So those are all good ways to go. I just presented things that I think are within reach, okay, relatively easily, but with big regulatory problems. Most regulators don't know what to do with fluid reactors.
Okay. Other question? Yeah, please.
That heavy metals contaminate slope, that 1 year later that grass start to grow. That is very impressive. My question is that grass is also will be contaminated by these metals? Or?
Less. Okay,
Yeah,
not
grass.
so where it will kill them. Okay, so if you remove cadmium from rice, it will still be cadmium, but much less. So we'll pass some threshold. One cannot think of regulating any form of waste down to zero. That's impossible. It would be infinitely expensive. But below what is reasonably safe.
Thank you.
Other question?
Another way to say this is many people think that nuclear waste is unsafe at any level, linear, no threshold. But that's like saying, if you take 100 aspirins, you'll probably die. So what if I take 1 aspirin a day for 100 days? Then they say you will also die. This is clearly not true. There is a threshold, okay? So there's some threshold. We need to find what that threshold is. It's not zero radiation. Radiation is everywhere, okay?
Yeah, Professor Ellis.
Frank, thanks for sharing these interesting systems with us. Has there been much investigation about whether some of these are amenable to catalysis that might change some of the chemistry you showed us? So you showed us mesitylene, for example, as a product that has different isomers. I mean, do those come out in some of the reaction conditions?
Yes.
Have you played with that?
Yeah, so mesitylene is actually only 71% of the yield from that. The other percentage, however, also hydrocarbons, so it's not bad. Right. Okay, they're not necessarily this very symmetric molecule. Or, you can tune the ratio. Yeah, you can adjust those ratios. Also, when I talk about salt as a interesting area for chemistry, it's like the following. Most of what we know about chemistry is based on solvents. Water as a solvent. Wash, right? We need to dissolve something, right? It's water. But water is hard to get above 100 degrees. So the reaction rates are slow. That's okay for biology. It should be, otherwise you start burning. That's no good, okay? But it's not so good for industrial chemistry. Salts are things that can take us as liquid solvent to hundreds, even 1,000 Celsius. And they have so many varieties, not just hydrogen plus oxygen. Anything from the left-hand side of the periodic table and roughly the right-hand side of the periodic, that's what we mean by a salt. Because they're from the two opposite sides, they're actually very good catalysts because it's very hard to change them permanently. They'd rather be bound to each other than something in between, right? So that's why there's this very large unexplored area that molten salt. So the two themes, if you heard nothing else, is molten salts are interesting things to look at, and carbon technology is interesting thing to look at.
So if not, let's thank again Professor Shu.
Synthetic order. 谢谢。谢谢。